have the suspicion that there can't possibly be another international dark sky reserve that's so close to a city with millions of people. It's only about 70 kilometers away. So Berlin's been around for quite a long time, and back in the 1700s, the Prussian Academy of Sciences thought it would be a great idea to have an observatory in Berlin. So they went to the king, who was sitting in Potsdam. That's where I live. He lived just a few stones throw away from where I live in Potsdam. And they went to the king, Friedrich Wilhelm III of Prussia, and said, we need an observatory. And he said, well, I can do that on one condition, as long as the observatory is open to the public at least 2 nights a week. And I think that's kind of an amazing thing, actually. That was already having citizen involvement in science way back then. At least that's according to the Wikipedia, so I hope this is actually true. So anyway, the part that's for sure true, I know this is true, they built the first Berlin Observatory about here, right in the center of Berlin. It's an area that nowadays, according to the World Atlas, is about 30 times brighter than starlit on a clear night sky. So it was built in the 1700s. Around the turn of the 19th century, they realized, okay, this is not such a good location anymore for us, so we need to move out of town. And they bought some land outside of town and built up a new observatory there. So that was here. It was a great location, right? That location now is 24 times brighter than a starlit night sky. So after a little bit of time, actually only about 70 years, they realized they had actually a problem again. Now, they probably had an issue with light pollution. I think that's probably true. But there was a bigger driver for why they had to leave town. And I want to know, does anyone want to try and guess what that might have been?
Coal smoke.
Coal smoke is, I suspect that was also a problem. But there was another problem that was even worse.
Fog?
No, not fog. Well, okay, Germany is not the greatest place in the world to do astronomical observations because of we have months of dreary skies, but it's another problem. So in a lot of cities, nighttime transit is a new thing. But in Berlin, actually, at the turn of the 20th century, they already had 24-hour transit. And as the trams would rattle through, it shook the ground and it disturbed the astronomical observations. So they needed to move outside of town, and this time they moved all the way to Potsdam. Now the interesting thing is, because the city had grown around the Berlin Observatory, the land was worth a lot of money. So they sold the land, and they got enough money to move out here to Potsdam, build a new observatory, and buy all the new instrumentation and still have money left over. So it turned out to be pretty useful for them. And that location is now about 6 times brighter than starlight. So you're not going to be doing deep sky observation there, but it now houses the Leibniz Institute for Astrophysics. So there are still astronomers, or astrophysicists anyway, working here in Potsdam. All right, so now the issue is, the problem is we don't know how light changed in Berlin over these years, right? So I'm going to make up a historical change in the sky. Well, it's not real, right? It's just made up by me, but it tells an interesting story. Now the good thing is that we can put 2 data points on here that we know for sure. The one is that nowadays, the limiting magnitude, so limiting magnitude tells you what the faintest star you can see is. So the higher the limiting magnitude, the more stars you can see. So in Berlin, we typically have in the center of Berlin actually limiting magnitude around 4, sometimes a little bit less, 3.5, but it's actually pretty good. We also know that since the first recorded reference of Berlin is in 1400, if we go back 200 more years and say 1200, there was nothing going on there. And so we can say, okay, the limiting magnitude was about 6.8, right? It's about as much as you can see in any location in the world. Now, in between is the problem. We don't actually know what happened, but we can sort of guess in order to tell a story, right? So Berlin was one of the earliest cities to be lit with oil lamps, and so at some point, say maybe 1800, it's starting to probably get a little bit of sky brightness. Then we moved towards electrification, and we had around 1900 or so the arc lamps that a lot of people were upset about because they thought that the very harsh blue color must be unnatural and unhealthy. We eventually moved to incandescence, and things started to get quite a lot brighter. Then came the World War, so I don't know for sure the history whether they had blackouts in Berlin, but presumably it must have gotten a little darker around that time. The war ended and electrification went on, and so things were going forward until Germany made a really terrible decision and put the Nazis into power. And one of the things about the Nazis that you might not have realized is that they were very interested in a modern modern society, sorry, speaking German. and progress and electrification, and they used light as propaganda often, right? So in that time period, I would suspect that Berlin probably actually became a lot brighter. So then came the war, and this time there definitely were blackouts. So it definitely got dark in Berlin. And after the war, of course, things got brighter. We had the divided city, but both sides of the city began to light again. Now, interestingly, in this period, when we had the divided city, they had to make different lighting decisions from each other, or they decided to in any case. So you can see this here on an astronaut photograph of Berlin, and I think probably many people in the audience have seen this, but you can still see the former division running here of where the wall ran. And so the reason was that in the East German state, money was tight. It was not a really wealthy country, and so they needed to use a really efficient light source. So they used sodium lamps, and that's the reason it's orange. In West Berlin, they actually really wanted to sort of stick a thumb in the eye of the Nazis. And so after the war, they reintroduced gaslighting as a sort of measure against the idea of Nazism. And because of that, actually, we still have a lot of people in Berlin who are really fighting for gaslit streets. And so you can see this is a neighborhood, actually 3 of us in the audience lived in or currently live in still. And you can see electrically lit streets here. And then these are the gaslit areas. And you can see that these, in comparison, okay, first off, these streets are probably darker than your streets in the United States. And so imagine how much darker the gaslit streets are, right? And there's a coalition of Berliners who've been fighting for decades to maintain the gas lamps. Even though environmentally it's a bad idea to use gas lamps, right? They need a lot of energy, they don't produce a lot of light, they produce other kinds of trouble, and if you drive a car into one, you gotta call the fire department, right? Because you could have a gas leak. So the city wants to get rid of gas lamps, and people are fighting against it. And so I think this idea that the public wants brighter is not right. What the public wants is light that makes them feel good about their neighborhood. And so we can see that in Berlin. It's just not true that the public always wants brighter light. So we come back to our fake trend here. And there's another interesting story here that involves German words. And you know, there's this meme that there's a German word for everything, right? So a couple of years ago, I did a crowdfunded project, and I needed to let people know about what it was about and on Twitter and things like that. So I invented a word, and this is the amazing thing, you know, being a second language speaker, it's actually possible for me to invent German words sometimes. So here's the word describing my project, which I think I invented, but I haven't. When I was looking at this last night, though, and I got a call on Josiana now, I think that I made a spelling mistake here. Do you see something wrong? Yes, that's right. Yeah, exactly, right here. It should have been Lichtverschmutzungsquantifizierungsprojekt, not Lichtverschmutzungsquantifizierungsprojekt. But even still, when you put it into Google Translate, it comes out correctly. Light Pollution Quantification Project. So good work, Google, on making up for my accidental spelling mistake. Okay, so it's great that we had a volunteer who's not the ones who've seen me give talks before, because I wanted you to also shout out, if you happen to know, what word do you use in German for a clear night sky? Do you have one or no? That's true, but there's a word for that, a single word. So okay, if you asked most Germans today, they would probably say Sternklar. And if we take those 2 words apart, it means star clear, right? So it's a clear night sky, you can see the stars here. If you talk to someone's Uroma, their great-grandmother or great-grandfather, they might use a different word for the same thing, which is Sternhell. And if you take those 2 words apart, it means star bright, right? And these 2 words mean exactly the same thing. They don't mean something different. They both mean a clear night sky. But you can see that there's kind of a difference in the sense of the word, right? What it sort of implies about the clear night sky. And the interesting thing is when you look at the history of the usage of these words in German text, so you can search them in the Google Ngram viewer. So what we see here is the frequency with which these words were used in German books. And it's very noisy, but what you see is that before electric lights, the Sternhell, the star bright word, was used more commonly. And after electric lights, the star clear became the more dominant word. And I think that's kind of an amazing thing to see. I don't know if this what this means or not, but I mean, you also see that during the war, both of those words started to be used a little more often. So I don't know. I wonder if whether in German literature there was more thinking about these dark skies during the times when they had the blackouts. Okay, so to come back to this, and now here we reach the problem of that we're associated with in this talk. We don't actually know what happened in this period, right? And we would like to know. So the issue is, and this has been a topic of the whole conference, right, is that the lights there are changing. And this could have been an alternate title for the talk. So here we see Calgary, Alberta, photographs from the International Space Station again, and you can spot areas where lights are changing. So for example, this neighborhood here is changing to white LED. There's another neighborhood here, there's a new subdivision up here, and one big change is that this is sodium, not LED, but you see that there's a ring road that's been newly illuminated. There's actually a very big fight in Calgary about the extension of this ring road because it passes near the Rothny Observatory and I think also a few sensitive ecological areas. Now one point, because I think this is the last point I'm going to bring up about the German side, but you know, I live close to Berlin in the state of Brandenburg, and the Berlin Ring Road goes around Berlin mainly through Brandenburg. It's about 150, 170 kilometers long. And on most of it, there are no lights. And on much of it, there's no speed limit. So why is it that I can safely drive around Berlin at 170 kilometers an hour at nighttime, and I'm not able to drive in Calgary, Alberta, 110 kilometers an hour without light? I think it's an interesting point. So we've all seen images like this. Apologies if you made it. I couldn't find who this really belongs to. But the point is we've seen lots of images like this, right? We know how to fix lighting, right? But here's a question and a challenge for you. What if we fix street lights? So here we have the beautiful Lumican lights, right? Perfect lighting. What if we fix street lights and area lights and light pollution just keeps getting worse? This is something that worries me a lot. So this is when we were flying over Berlin one time. We happened by accident to fly through a searchlight. This was during the Berlin Festival of Lights. And you can imagine what it's like for a bird when it happens to be in that path, right? It's a really amazing thing. Now I want to show a concrete example of this problem from this region we're in, and I have to thank, I'm not sure who tipped me off to this, but in one of the talks somebody pointed this out, so I decided to make this graph. This is the area we are sitting at the pin here. And this is an image from a new web application that I'm currently developing with European funding. And what it allows you to do is to draw an area around something and look at the light trends. So watch your mailboxes when this is ready, maybe in April next year or so, then the IDA will definitely let you know about it. So apologies to our hosts. I didn't know exactly where the boundaries of Salt Lake City were, but I drew approximately there. And we can look at the trends in Salt Lake City. And we see, so first off, the vertical scale here is the units that the radiometer measures in, nanowatts per centimeter squared per steradian. You don't probably really need to worry about that. It's just a number. If it's bigger, it's more light. You see that there's these jumps up in the wintertime, and that's because when we have snow, everything gets a lot brighter, right? So we tend to throw those data points out and mainly look at the data in the times that it's easier to understand, so in the summertime. So you could see that here the average for Salt Lake City is something like 25 in these weird units, okay? Now let's look, and this is what I was tipped off to. What is this down there, right? Growing tomatoes. So before we come to the answer, let's look at the light trend, okay? So there was nothing, and then all of a sudden in 2015 it jumped up. And remember that Salt Lake City on average had a value of like 20. Right? And now you're here up between 1,000 and 2,000, so like 100 times brighter than the average for a town. So it got called out already what it is. It's not this town of Mona, it's something over here, and the nice thing is that with Google Earth we can take a look at what changed and see that in between 2014 and 2015 the tomato farm was built. So greenhouses are something we need to really have on our radar, I think, right? And you can see these images. These are photographs from my colleague Florian Tornow, and Camille Spolstra took one from the ground. This is still twilight, and you can see already that you're seeing the sky glow, right? These things are incredibly brilliant. And this is a huge waste of energy, because if you just put rollers over top, you would keep the light in, and you could use a lot less light. Right? So this is one of the most clear examples of waste light that exist on Earth, and these are among the brightest objects on Earth that we see anywhere. So how do they compare, though, to the whole cities, right? So with the new tool, it's real easy. We just draw a block around Salt Lake City. We can see that in those units, the total is about 150,000. If we take Ogden and North Ogden, then you get about 35,000. I apologize to the host. I don't know the names of these communities here. Together, they make up about 38,000. If you take that greenhouse all by itself, it has in those units about 50,000, right? So let's say we replace all of these streetlights with Lumacan, right? And you've got this going, and this is already about 20% of the light emissions from this whole region. This is something we need to be really, really very concerned about. So there's a question that has been motivating me for quite a while, is that with the transition to LEDs, we know that we can make things better. On the other hand, we have things like the greenhouse popping up. So is the world getting brighter or darker as we transition to LEDs? So we answer this with the satellite data. Now you've probably all seen maps like this. This is actually a total fake out, right? Europe never actually looks like this at night. It looks more like this. So this is Europe on a moonlit night. You can see the reflections from the clouds. And you can see that the ground itself is actually quite bright in the moonlight, and you still see the cities. So our colleagues from the US National Oceanic and Atmospheric Administration take these maps. They find the times when there is no moonlight and no clouds, and through that they build up a monthly composite, and then you end up with a map like this. So this is built up of data with no moon and no clouds, and that's what we can then analyze to see changes. So here, in order to help you understand what I did, is an image of Berlin. And so we have here, this is the Tegel Airport. This is the Zoologischer Garten that was downtown back in the time of the divided city for the West Berliners. Here's Potsdamer Platz and the Reichstag and the Brandenburg Gate. And here is the other downtown for the East Berliners, Alexanderplatz. And what we have down in the bottom right is sort of the black eye of the Berliners. I don't know how many people realize this, but this is Berlin-Brandenburg International Airport, which was scheduled to open in something like 2012, I think. They had flights booked, and about a day before the airport opened, they said, oh, we're not opening. And it's still not open. And the date keeps getting pushed forward into the future for when this airport will open. But the lights are on. And have been on. In fact, back in 2012 or whenever it was, they couldn't figure out how to turn the lights off during the daytime. So they were on all the time. So there's no passengers at this airport. But it is lit nonetheless, right? Okay, so let's use Berlin-Brandenburg International to help us to understand what I did. So we did two main analyses. The first was to ask, how does the lit area of the world change from 2012 to 2016? So what we do is we define a threshold in these units of numbers from the day-night band. So we say if it's brighter than 5, remember that the average in Salt Lake City was 20. If it's brighter than 5, then we count it as lit. And then we add up, how big is this pixel, right? And we add that up to the area for Germany that's lit in 2012 or 2016. So that's pretty easy. Slightly more complicated is we want to understand, for areas that were already lit in 2012, did they become brighter or darker? And so what we do is we take one of these pixels and we check, was it lit in all 5 years, 2012, 13, 14, 15, 16? And did it stay relatively stably lit, right? So we're talking about, not talking about things that change in brightness dramatically, that could be like an oil flare or something, but rather, was it probably more like electric lighting? So then we can compare how bright all of these areas were in the country in 2016 to 2012. And we also did some analysis on the relation to GDP, but I won't talk about that unless someone asks a question. All right, so before I can get to the answer, though, I got to tell you a little bit about the satellite. And this has come up in a lot of the talks in the last couple days, but I want to make sure that everybody really understands this, because once we release this app for you guys to look at your own trends, you're really going to have to know what you're looking at. So there's a problem with the sensitivity of the satellite. And it has to do with the spectrum or color of light. So when we look at the spectrum of a white LED, now this is what everybody uses because it's on the Wikimedia Commons, right? But actually, this is a very cold white LED. And even 3,000 Kelvin or 4,000 Kelvin doesn't look quite as bad as this. But in any case, you can see there's the blue peak, and then you have the longer wavelength light. Now, when we look at the spectral sensitivity of the satellite, that means what colors is it able to see? I can put that here, and I've stretched these two plots so that they're the same, and I'll draw a line here. And you can see that the satellite is completely blind to all of the blue light. But it actually has sensitivity in the infrared, which is where sodium actually has an infrared line that we as humans don't see. So this is kind of a huge problem, right? And what it means is that if you switch from high pressure sodium to white LED while maintaining the total number of lumen output, you will end up looking darker, most likely. And we can see that concretely in an example from Milan in Italy. So these are astronaut photographs. I forget the year exactly, but you see that Milan was orange and the outskirts of the city were orange because everything was lit with high pressure sodium. And when we fast forward a couple years, Milan becomes white because it's lit with LED, while the outskirts remain orange. And the brightness, according to Alejandro Sanchez de Miguel anyway, stayed pretty much the same. Now when we look with the satellite, so remember we have lower resolution, these are astronaut photographs, they're fantastic, but they don't cover the whole world, right? The satellite has the advantage that it covers the whole world, but it means that the pixels are much bigger. So when we look with the satellite and see how did it change from 2012 to 2016, the blue areas are places the satellite said it got darker. The yellow areas are places where it says it stayed the same, and the red are areas it says that it got brighter. So we think when we look at these satellite data, it looks as if Milan got darker, when in fact it didn't, and if from a perspective of dark skies, the color is even worse, right? So be careful when you're analyzing the satellite images is one of the messages. But nevertheless, when we look worldwide, what we see is that almost everywhere is getting brighter. So again, on this scale, blue means that the country got darker. So you see, for example, in Syria, because of the war, lots of lights went out. And red means that the country got brighter. And so you see, especially in the developing world, that it's brightening rapidly. Now, in the developing world, there's 2 points to make here. One, it makes sense that it's brightening rapidly because many of those people have been living without light and without electricity, and we have to respect and even applaud that they're getting electricity. We would not be willing to live without having outdoor light in our cities. The other thing to point out is that, so in this map, United States basically didn't change, right? Maybe it increased by a tiny amount. It's not enough to be shown. But a small increase in light in the United States is this is a proportional thing, right? So a small increase in light in the United States might be more than the entire increase in the country of South Africa, right? So this is, we see that they're brightening most rapidly, but that doesn't mean that that's where the most lights are going in. Now we see in the European countries actually that most of them are still getting brighter, and worldwide most countries are getting brighter. And remember that the satellite has no sensitivity, or it has reduced sensitivity to LEDs, and we know that LEDs are going in the United States. So that means that absolutely definitely United States got brighter. We just can't quantify with this satellite by how much. So this is a lower limit for each country on how it's brightening. And we have very similar results for area. Both of them grew on average about 2% per year per country. So why is light growing? Like, why is Germany, why is France getting brighter when we know that we're putting in better LEDs? Well, one reason is that there are simply new uses of light. So for example, this is a video screen in Berlin, taken 2 photographs with different exposures in order to show how incredibly bright this was, right? It wasn't dimmed. And it was a real problem. In fact, the good news is that this is now dimmed at night, and actually it's totally fine luminance now for that region. I was there just 2 weeks ago with some journalists who were very disappointed that it was dimmed because they wanted to be able to reproduce this for a show that they were making. What you don't see is that on this street there are now 2 little smaller video billboards for the pedestrians. Now, LED is an energy efficient technology, right? Produces light really efficiently. But those video screens play during daytime, not only during night, right? So the idea that LEDs will save us energy, it only makes sense if we're doing replacements, right? Because in the past, advertisements would have needed very, very little energy, right? Someone drives there with a van and plasters something new up. Nowadays, you have an LED that's burning energy in the daytime and then burning energy again in the night. So this is why LEDs, when we look at a national scale, don't necessarily save energy. And another point to make with these new uses of light, if you search on Google for bridge lighting, what you see is that it's no longer the case that a bridge is a device to take you from one side of a river to another. It has to be a light show, a light spectacle every night, right? Now, I'm not claiming that bridges are the reason that countries are getting brighter, right? That's surely not the case. The point is that LEDs allow a lot of new applications of light that we didn't have before. This enriches our society, right? We shouldn't forget that. But it can also mean that we produce a lot of extra light pollution. And we need to find ways to use LEDs that are effective. So that was all about light going upward into the sky. But for our community, what we're particularly interested in here by light pollution, what I mean is sky brightness. This is an editorial that I was very pleased that editors of Nature Astronomy invited me to write. Is light pollution getting better or worse? And here I address a problem with the methodology that we use to measure sky brightness. And this is really the heart of the talk now. So I'm going to skip through this because I want to have more time for questions, and I think everybody knows it, right? So blue light is problematic because it scatters more in the atmosphere. The other point is that when we use night vision, we're using our scotopic vision, right? And you see with high pressure sodium, there wasn't a lot of light there in the main area where we have scotopic vision. Whereas with LEDs, we've put a little more light out in these regions. Okay, so LEDs are bad, right? That's the thing that people would say. That's obviously not the message that we really bring across, right? But that would be the really naive understanding of these two facts. But there's a problem now, okay? Because we know that this is my hometown in Wetaskiwin, Alberta, in Canada. We know that when we do an LED replacement, even if people choose a lamp that many of us wouldn't choose, so this is 4,000 Kelvin, it has although a really fantastic cutoff, right? It's not just full cutoff, it's really, really strong cutoff. So you see that as you drive, the lights seem to pop on and appear as you come underneath them, right? And this is really fantastic. This is much better than full cutoff when you have something like this. And you see also that they did a great job. This is an agricultural field. There's no more light spilling out there. And in the past, with the sodium lamps that were with Cobra heads, I guarantee you this whole area would have been illuminated, right? So here's the question. We put in 4,000 Kelvin white LEDs, right? That's bad because of the scotopic vision. It's bad because of the extra scattering in the atmosphere. But there's a lot less light total because it's constrained more, and we're not putting any light directly into the atmosphere. So did things get better or did they get worse? Now, when we try to answer that with devices, we have the issue that we are not accounting for the fact that in a big city like Berlin, and you're looking at the sky, you're probably actually going to be using photopic or at least mesopic vision. And when you're in a darker place, you'll use scotopic. So how is the camera or the SQM or whatever you're using supposed to account for the fact that human vision is changing its sensitivity? It would be very difficult to do that. Probably it could be done, but it would be difficult. But in my opinion, the right thing to do is simply ask people. Oh, I skipped ahead of myself. I want to show an example, which is exactly what I'm coming to. So the point is, what if in the red component of light we get a lot better, but in the blue component we get worse? How do we decide whether that was an improvement or whether things have actually gotten worse? So this is an example of a photograph from Zoltán Koláth. And the V stands for visible. So this is like the green range. And this is looking horizontally at a town in Hungary that had a lighting retrofit. Before they had high pressure sodium lamps, but with Cobra fixtures that had something like 5% uplight, right? So they were pretty bad lamps. And they switched to white LED. I don't remember the color temperature. So in the visible range, you see actually things got better. When we look at red, you see that things definitely got a lot better, which makes sense, right? Because sodium lamps are pretty orange. And then when we look at the blue, actually things still maybe did get a little bit better, right? Because they have the really sharp cutoff. Now you could imagine in another community, you could have the situation that red got a lot better and blue got a little bit worse. And then how do you decide whether it's an improvement? And my perspective is we simply have to ask people, how many stars can you see? How many stars did you see before? How many stars do you see now? So the problem is we don't have these visual observations going back into the past. This is just a big question mark, but we can start doing it now in about, at least from 2006, we have data from the Globe at Night project. So who's taken part in Globe at Night before? Okay, and who's taken part in Globe at Night this year? Okay, it's a lot fewer. Last night? That's great. So we have a problem that we don't have enough people taking part in Globe at Night, right? And if we want to track how light pollution is changing over time, how sky brightness is changing, we want to cover this curve. We want to know what's going on. So if it's getting worse, we can let the policymakers know. If it's getting better, we can also let them know. It's working. We need to continue. But if people aren't making observations, then we're just going to be in the question mark region again. Now, in case anyone has never heard about globe at night before, I want to explain how it works. So the idea is that you look up at the sky and say which star map matches what you see. So for example, in February, you might be looking for Orion. This would be maybe in Bryce Canyon. If you're in downtown, if you're in Berlin, the central Berlin, actually, you probably get the fourth star there, getting towards fourth magnitude, could be third magnitude. You say, which of these matches best? And when I first heard about globe at night, when I was a arrogant young physicist still, I thought, okay, this is crazy, right? This is not real. This is not a real measurement. It's just people's subjective opinion. That can't really work. And I had the luck that at some point I had a student who wanted to work with me together on looking at the globe at night data. And that turned me into a complete convert, and I realized how incredibly wrong I was beforehand and how important it is, the work that Connie's doing. So this is a paper from several years ago where what we're showing here on this axis is how bright the satellite, that was the older satellite, said the region was. So you can see Beijing is over here, Sark Island is down here. And up high, we have a high limiting magnitude. That means you can see the very faint stars. Down low, you can only see the very, very bright stars. So what we see is that in aggregate, the globe at night data shows that people do a good job of measuring how bright their region is. When you look at individual observations and compare them to this line, because you can't say 3.5 in globe at night, it's not possible. So someone says 3 and you compare how far away they are from that line. And we build a histogram of what it shows. We see that the individual observations are really not very precise. And that was exactly what I was worried about earlier, right? So you're not really going to be able to use globe at night to see how your backyard is changing. But you can use it together with all your fellow citizen scientists to understand how maybe your state is changing if you have a huge number, or your country, or how the whole world is changing. Now, if you're really dedicated and you want to take it to the next level and really understand how your backyard is changing, you can potentially use my app, the Loss of the Night app. The way this works is instead of asking you to look at star charts, we'll actually direct you to an individual star. So here you can see this little pointer on Polaris there. We're asking you to say whether or not you can see Polaris. And if you can't see it, you can say, well, I can't see it because, my neighbor's house is in the way. I'm looking too far down. Or you can say there's clouds, or I'm not sure, or you can say it's simply not visible. And one of the beautiful things about this data is we can check the self-consistency. So we can know whether or not someone is really understanding what's going on. So in these graphs, what I'm going to show, time is going this way. So the first star, someone looks at it here. The last star is out here. And again, these are the very faint stars up high at high stellar magnitude. And these are the very bright stars down low. So let's start with an example of someone who didn't do the most accurate observation ever. It's a little bit hard to see the black stars. So the colorful stars are the stars they said they could see. The black ones are the stars they couldn't see. And it worked out kind of okay, right? But you see here is a relatively bright star that they said they couldn't see. Here's a fainter star they said they could. So it doesn't make so much sense, right? So we can draw a pretty large error bar and say, well, probably sky brightness is around somewhere in this range. Other observers, the more you practice using the app, the better you'll get at it. They make more accurate observations. So here you see that every star that the person could see was brighter than every star that they said they couldn't see. And so in about a 5-10 minute period, you can do an estimate of limiting magnitude to about 0.1 magnitudes. If you're super dedicated, then you can continue way past the 11 stars shown here and go out to 35. And I don't have the circles here, but you can see here's the stars that weren't seen. We can have a lot of confidence. This is a very, very clear measurement that that person is telling us exactly where the limiting magnitude is for them. So if you're to do things like this, you could probably really see how your backyard is changing. A few caveats. One, limiting magnitude is not the same from night to night, which we've had several people talk about in breakout sessions. Also, not only in the very far away places, but also in the middle of cities, it changes. So you're going to want to have several measurements. The second is you see the scale only goes up to 5. It makes no sense for me to send you out to Bryce Canyon and ask you to turn on your phone because it's going to blind you. And then even if you've got your phone then later inside the app, it goes into a red light mode. When I ask you, can you see that star there? You're going to be like, which star? There's stars everywhere. I mean, I don't know. So this app is for when you are in your suburban or urban areas, okay? So I really want to drive home this point. For us as a community, it's really critical that everybody take part at least, say, like twice a year. And from your home location, and once in a while when you travel, it really only takes about 5 minutes. Almost all of us love to go outside and look at the stars anyway. So just when you go back inside, sit down at the computer and record with Globe at Night what it is that you observed. So after you've done your observation, you can see it a day later at myskyatnight.com, which is another web application that we developed. You can see their SQM measurements. If you have an SQM, you can submit your data to Globe at Night. If you want with the SQM, you can use the Loss of the Night app to put your data in, and then it'll automatically find your location and know what the time was. And then you'll be able to see everything at myskyatnight.com. So yeah, that's kind of the end of the talk. I have one last point, though, which I'm a little bit worried about doing. But I've been thinking that, it's an activist meeting, right? And folk music kind of belongs to activist meetings. So I can't believe I'm going to do this, but I'm going to go for it. Come gather round, people, wherever you roam, and test the sky brightness to see if it's grown, 'cause if you don't, it'll just stay unknown. If the stars to you are worth saving, then you'd best start observing before they are gone, for the lights, they are a-changin'. Thank you for not laughing.
Okay. It's interesting that you have touched on an aspect of Globe at Night that has bothered me too, which is I'm asking, and I have been doing religiously because I teach a high school astronomy class. I've asked them every time I teach the class to make Globe at Night measurements. It works at so many different levels. And I've often wondered, well, we're just asking them to do it, people who are not used to observing, to the nearest magnitude, because the charts are pretty crude. This is an awfully hot mic. Can we turn this down a little bit? Thank you. And you've renewed my confidence in the program. And is Connie here? Connie Walker?
At the front.
Yeah. I think Connie deserves, now the mic's dead. I think Connie deserves a lot of credit for the many years that she has pushed Globe at Night. Because this is our best tool for getting people to look up and do something meaningful. And so I applaud you to think deeply about this and to give it your researcher stamp of approval for us to go forward and actually expand. My sense has been that the interest in Globe at Night has kind of waned and waned and waned. And I look at the maps and see, there were, so far up until my class did, there were 10 observations made in all of Greater Boston, and I thought that was really sad. So my goal now is to go back and make it 10,000. I don't know who will know what. Anyway, this is great. Let's open for questions. There's a mic here so that you can please line up, and Ollie's turning it on, so we'll be sure to hear you. And our first questioner is
Amanda.
He hasn't turned you up yet.
Oh, okay.
He turned you on, but not up.
Is that good?
Yeah.
All right.
Please introduce yourself.
I'm Amanda, Communications Director at IDA. And my question is relevant to my position at IDA, thinking about expanding the avenues of entry into our work and helping people understand that the quality of night itself is something that we all want to respect and take care of. At the risk of threatening the fact that our theme of this meeting is looking up and looking at the stars, and that's something I'll appreciate. A lot of this conversation is about measuring the impact of light pollution on how we see the stars, right? And I'm wondering if there's been any conversation about other metrics that expand that conversation and think about the quality of night in general, and make it broader than just what we see in the night sky.
Sure. Can we jump forward, Ollie, to slide number 76, and I'll show you one of the tools that I use when I'm giving presentations to to different people. All right, so is that the start? Okay. Who's seen this before? Who hasn't seen this before? Great. I think this is one of the most powerful tools we have for communicating the issues, right? So the idea here is that the square marked A and the square marked B are exactly the same color and brightness. The cool thing is it has nothing to do with this green object, right? They still look different, but with PowerPoint it's really nice. You can bring them together. They're exactly the same. No one has any idea how bright anything is. We react only to contrast, right? So then I follow this up with this really great, our friends in Troy, sometimes they do things that drive us crazy, sometimes they do things that make us very happy. I see, okay, so I can follow this up, right? So what are the problems? Why are cities dark? The three problems are glare, non-uniformity, and overlighting, right? So lights are what makes cities dark. So here's from our friends in Troy. They did an experiment with their parking lot where they put in LEDs, therefore you can brighten and darken it, dim it, turn it off instantaneously. So if they turn off the second row, they can reduce the uniformity of the parking lot. From 3 to 1, that means that the brightest place is 3 times brighter than the darkest place, to 10 to 1. So the brightest place is 10 times brighter than the darkest place. They ask people to go in the building, and they change the lights. They come out, walk around a bit, and say, how do you feel? How good is this lighting? How safe does it make you feel? And what they show, photographs lie, right? This area is lit, right? We all know that. But what they show, so over here, this is when the researchers make it brighter. If people say it's good lighting, it's up high. If they say it's bad lighting, it's down low, okay? So what they show is that when you have uniform lighting, it's very rapid that people say it's good, right? And it doesn't get any better, right? It doesn't matter how bright you make it. Once it's lit, it's lit. With the non-uniform lighting, and 10 to 1 is actually better than the recommendation, right, Nancy? It's 20 to 1, I think, is the minimum recommendation for parking lots in the US.
By the way, there's all new research at Virginia Tech that has debunked all of this. So I'm just letting you know.
All right, okay.
But I didn't want to mention that.
Okay, but the point at least that you reach it very early is there, right? And so the difference is this is 1.9 kilowatts consumption. This is 240 watts. And so if you have more uniform lighting in parking lots, I'm not talking about streets, but parking lots, you can use a lot less light. So I like to use that combination of things to try and demonstrate that this is about having good visibility in our city and feeling good about the place. It's not necessarily first about dark skies. So when I give talks, typically actually I come up with all these reasons for why we need to improve lighting, and at the end I say, and if we do that, we might be able to see the Milky Way over our cities again. So I come to dark skies at the very end.
What the new research is in Virginia Tech?
Yeah, hand it over.
I'm sorry, I just can't get up. The new research at Virginia Tech completely agrees with you. It's 100% contrast. That lighting level has nothing to do with it. In fact, even non-uniformity may be better because the object could have higher contrast against a darker background. So it's a whole new metric versus just horizontal illuminance. So it's amazing research, and the lighting levels are going below.
So from my naive face in the crowd perspective, I'm not sure that's a good thing, because if I'm understanding what you just said, to get better uniformity, you need more poles, more lights. No?
It's the opposite.
The opposite of what he just showed. You want the... All right. Okay, so do we have, we still haven't gotten the... I'll just use this. All right.
I can constrain myself to stand.
You stay here, and I'll be the face, I'll be the mover.
Hi, this is Tim Hunter. What a wonderful amount of work you've done. I think there may be a little bit of misconception on LEDs. I don't think they're actually all that energy efficient compared to low pressure sodium, high pressure sodium. I think the reason that they become so popular is because they can be directed better, they last a whole lot longer, so the replacement costs. The one thing that I've noticed, even in very good installations, is when you're near them or under them, the glare is worse because they're actually a whole bunch of small point sources.
Yeah.
You want to comment on that?
Yeah. So the point about LEDs being more efficient is much more true when you're talking about indoor lighting, right? So I tell the journalists this all the time. One of the advantages of LEDs is we could have a half-watt LED or a 1-watt LED that we couldn't have done with sodium, because sodium was incredibly efficient as long as you make a lot of light, right? And so LEDs offer us the possibility of having completely new models for how we light spaces. And what we've done is we've taken a like 17th century technology, which is the light pole, right? And we've put a 21st century lighting technology on top of it. So it's not surprising that we get bad results. We're not using the technology, the abilities of the technology yet. And so when you see, it's true that high pressure sodium is a very, very efficient technology, but if we want to go down to 1 lux instead of having 20 lux on different spaces, then LEDs will allow you to get there. And again, it's not about, luminous efficacy is a terrible measure of energy efficiency. The number that we need to think about is watt hours per year, or watt years, basically. That's the number that really matters in terms of efficiency.
Thanks. Hi, Chris. Ted Blank from Fountain Hills Dark Sky Association. In your app, which I love, I just installed it. Is there any recommendation on how long you should wait to get your eyes night adapted before attempting to see the stars to be more uniform in the results?
So, as I said, because it's for urban and suburban locations, you're usually going to be a place where you're not going to completely dark adapt anyway. And you will, in very many cases, need to be looking with your arm screening out nearby light sources, right? So I did this in the center of Brussels recently, where when I walked out of the train station, I thought, okay, I can't see anything, but I'm going to do this, right? I'm going to look crazy. I'm standing in front of the train station, going like this, and I've got the app out, so people are looking, and then they would see I'm looking at the stars, and they're like, oh, okay. So it turns out, actually, in the center of Brussels, limiting magnitude is like 3 or something, right? So our opinion, and when you hear people say, you can only see a handful of stars in my town, it's simply, in my opinion, not true. I've done observations in Athens, I've done observations in Mexico City, I've done observations in Brussels, and I don't think I've ever seen a limiting magnitude less than 3 once you try to screen out the glare. So to the question of how long do you have to wait, one of the things the app does, we start always with the brightest star in the sky that is above 45 degrees above the horizon, and we go at the start with a little bit brighter stars. And then slowly go to darker ones. So I think that in terms of going outside, turning on the app, loading the app, looking at the first star, your eyes have already started to adapt, and then you just got to screen out, and it'll work okay. So I haven't seen evidence in my own observations that I start to make a different decision over time, right? That I'm later saying that fainter stars are bright. So I think that the adaptation actually is not that much of an issue.
So we're basically out of time. I'm sorry, but I just do the hamster talk, please.
It's about 5 minutes long, though.
Well, then don't do that.
All right. Should we do it? Yeah. All right. So let's jump there. I'll do it as quick as I can, okay? So hamster, so pound hamster, we got to check this out actually whether it works. Years ago, because I was giving this talk a lot, at the end I always had a call for the people in the audience to join IDA, and there was actually like a discount code. If you type pound hamster, you got a discounted membership. Okay, so the idea is I start off with saying I'm from the German Research Center for Geosciences. Why does anybody pay me to study light pollution? And I come up with this. You know, the light pollution can kill you, but there's fine print somewhere if you're a hamster. Okay, so how can light pollution kill you if you're a hamster? Well, I start off with a history of light on Earth, and I say, okay, here's a satellite picture of Earth from 1 billion years ago. There were no lights, but it's a very boring time because beer hadn't been invented yet. On the plus side, there were no dinosaurs. That's pretty good. The reason there were no dinosaurs is that sex hadn't been invented yet. And so we definitely cannot talk about sustainability in such a planet, right? So then I jump forward through time with a bit of jokes about, okay, so now sex has been invented, but it's who knows, some kind of weird insect sex, right? So nothing that interests people. And I jump forward some more, eventually at 65 million years ago, you're glad that Earth is dark because it means that you don't see the dinosaurs that are coming to eat you at nighttime. Then we come to 5 million years ago. Now there's lots and lots of sex going on among the little mammals, right? So this is about the time that primates split apart. So sex is real good for the primates to differentiate and make new primates. So we turn up on the scene. And about 5,000 years ago, civilization developed, and we know that because, beer was invented, so that's the sign that we have civilization. The downside of civilization is you get a bill at the end of the night, right? So here's a Sumerian tablet with a bill for the beer, right? So then I come to about 1400 and admit that, okay, this is not really a satellite image. We didn't have satellites, we can't go back in time. But this is when the first lights would start showing up because of oil lamps. So, and now we're starting to really have to worry about sustainability. So then I jump through to, this is Europe now, and then I talk about why is light a problem. So we have experiments where the researchers have the treatment that there's light in the daytime, light at night, or light in the daytime and darkness at night. I talk about the experiments from Laura Fonken. That's really excellent. They feed the animals the exact same amount of food. Right, it's little pellets, but the ones that are exposed to light at nighttime end up getting fatter than the other ones. I talk about, this is not strictly about light, but it's about how jet lag influences you. So the different sets of hamsters, well, they're not really hamsters, but the different sets of mice or whatever they are, one gets just regular light-dark cycle, the other one once a week has a simulated flight I drew the airplanes wrong, to the west, and the other one a simulated flight to the east. And what you see is that the pregnancies are successful 90% of the time when they have light-dark cycle, only 50% of the time when you're flying to North America, and only 20% of the time when you're flying to Europe, because jet lag in the eastern direction is so difficult on us. And finally, I end with the experiments from Abraham Heim, where they had a field experiment now, where they had a problem that the farmers wanted to deal with these voles that were eating the crops without using poison. And so Abraham Heim and his collaborators had the idea we could put some lamps up on the field, and then because they breed when the season changes, they wouldn't realize it's breeding time, and they would eventually just die out. So they did the experiment. The group that's under the sun and the moon, they had lots of babies. That was exactly the problem, right? And the group that was under the lamps, every single one died. And so they were totally shocked. So they said, well, let's try that experiment again. This time we'll only turn this on for 15 minutes every 4 hours during the night. And all the animals died again. And so it took them a while to figure out what's going on. They went back to the lab. And what they realized is that the animals were tricked a lot more than expected. So in addition to changing the time that they breed, they need to regulate their temperature. Because they thought it was summertime, they were burning way too much energy, and they effectively all died of exposure, even though in the exact same environmental condition except for the light, they could have lived and reproduced and everything. So oh yeah, wait, so why do we talk about hamsters? Why do we do research on mice? Right? We are also mammals, and similar things are going on in humans. So that's the hamster talk in as brief a time as I could make it. Thank you very much for extending with the extra time.